Welcome back, everyone. We got most of the people, which is good. This is the second part of our last training session here, and we're going to be touching on PID loops. So as you can see up on my screen, there is just kind of a little process diagram of how a PID loop works. So it's a closed loop controller. Essentially, we control an output to try and reach an input, or to try and make an input reach a set point. We're going to be talking a little bit about the theory behind PID loop and how they work. It's going to be a repeat for a lot of you guys. I'm sure many of you have been using these for years. Then we'll jump into Sysmac. We'll show you where you find the PID loop in your toolbox. We'll go through setting up a program with a PID function block. We'll set up our tags. We'll look at the structure. We'll get everything configured before we actually do any simulating and testing. And then we'll actually get into testing these things with our simulator. And eventually we will build a simulated feedback loop, so it actually lets us use the auto tuning function in the loop itself. So a PID loop's job is to bring a value, which in Sysmac we call that the PV, the process variable, to a set point, which we call SP, by manipulating an output, which we call MV. And what this does is allows for variations in the equipment or process, and we compensate for those variations to keep our input in line with our set point. So the set point itself is something that the user enters, possibly from an HMI. It could be from a panel-mounted potentiometer. It could be hard-coded, and the user has nothing to do with it. But this will change from time to time along with the changes in the process. So the PID loops are constantly recalculating, reevaluating, and adjusting to changes in either the set point or the process itself. The process variable is the input. This would commonly be a transmitter of some kind. If this was a flow loop, it would be a flow transmitter. I'm going to say we're programming an oven today, so this would be the temperature probe in the oven. And then the manipulated variable is the output. So our PID loops give the output in an analog value, but this is commonly converted into a digital value, and we treat the output as the duty cycle. So the input has to be analog, but the output we can make digital if we really wanted to. And I've seen this in some heating applications. Let me back up a bit here. Okay, so let's jump into Sysmac, and we can open up the project that we had the last few days, the last few training sessions. Give everyone a few seconds to get theirs loaded up. Okay, so what we're going to do is go into our Multiview Explorer, and we're going to go to the PLC, and we're going to go down into our programming, and we're going to add a new section into our program 0. And I'm just going to call this Oven PID. I'm just going to rename it and call it Oven PID. We can go ahead and open that up. Now, just like we did on the first or second programming session, I don't exactly remember, but I'm going to be doing this from the perspective like I've never done a PID loop in Sysmac Studio. So we're going to be using the help file the whole way, just to get you guys familiar with that. So if I didn't know where to find a PID loop or how they worked in Sysmac Studio, I would just search for it in my toolbox. Then you can see here, I typed in PID and we've got two options. So PID AT and then PID AT heat cool. So the heat cool block is obviously something you use in a heating and cooling application, but it essentially is 2 PID blocks in one. Now we can change our PID AT block from direct acting to reverse acting, but the parameters, the tuning parameters, are going to be the same for both of them. Where these differ is with the heat cool PID block, you actually have heating tuning parameters and you have cooling tuning parameters. So to keep things simple today, we're just going to use the PID AT function block. So we can go ahead and drag that onto our rung 0 on our new program. And the first thing I'm going to do is just populate the tags on this block. Since in Sysmac, it fills in the data types for you. These all have defined data types. I'm just going to go ahead and name everything. You can use my naming convention if you guys want to use your own. Go right ahead. So I'm just going to name it here. You guys play along on your end, and then we'll move on at the end here. Okay, so I've put my PID block into my logic. I've populated all of the input and all of the output parameters on it with some tags. And now I need to figure out what exactly all of these input and output parameters do. So I'm going to hit F1 and go to the help file for that function block. Now most of these are, I mean, just from looking at it and the shortened tag names, I know what a lot of these are. If you mouse over them, they give descriptions. But the ones that we're really going to be looking at today that aren't so self-explanatory are the OPR set params and the init set params. So these are structures, custom data types, just like we made the other day. And all of the members of these need to be populated with values. So these are essentially everything from tuning parameters to scaling parameters to auto-tuning configuration parameters. And what's nice with our help file is they are all very easily located and decoded, if you will. So scroll, excuse me, if you scroll down about a page, we get to a section called structure specifications. And this is where we break down the OPR set params and the init set params, and we can see how many members are in here. Now, there are a few ways we can set up these. If we were online, we could actually use the watch tab page table, which will allow us to access individual members of the structure. So if I put operator params in there, so here you can see if I was online with the PLC or if I was running the simulator, I could actually manually enter values here directly into the memory. But what I like to do in situations like this, and we did this, or I demonstrated this on the Modbus as well, is I like to put a rung above it and use an inline structured text box. So if you just right click on the rung and choose insert inline structured text, this is a nice way to have all the values right in front of you so you can see what they are. And if we need to change anything, I'm going to be using constants, just hard-coded constants. We can easily online edit these if we need to. So to make a comment in structured text, 2 forward slashes, and I'm just going to put a little note here about what this inline structured text box does. So now I'm going to bounce back and forth between the help file and my logic, and we can set up each member of the OPR set params, and then we will do the init set params. Now in other platforms, this is set up through double clicking on the function block. That's in the Rockwell world, that's how they do it, but you've got very similar parameters you have to set up. It's just in Sysmac, you code it like it's any other variable. So the first one in our list here is the MV low limit, or manipulated variable lower limit. That one's pretty self-explanatory. So that's our output low. Now I'm going to keep everything 0 to 100% on this, on both the input and the output, to keep things simple. So we'll do the low limit and the upper limit right now. We'll just set it 0 to 100. So our tag name, once I start typing it here, should autofill. And if I hit the period, it's going to let me access the sub-members of it. So the first two we'll do are the MV low limit and the MV high limit. So structured text, to make a value equal to something, you use a colon, and it types a colon and an equal sign automatically. So we'll make our low limit equal to real #0. And in structured text, we finish the line with a semicolon. Now we're going to go back and do the MV high limit, and we're going to make that 100. If anyone's running into any issues, it's a good time to speak up now. Type it in chat or just unmute yourself. Otherwise, we'll keep going. Okay, so we've got our lower limit and our upper limit. I knew they were reals, by the way, because in our help file, it specifies the data type of each of the members of the structure, as well as the valid range, and in some cases, a default value or recommended starting value. So the next one is a manual reset value. So if we read through the description here, the value of our manipulated variable when the deviation is 0 for the proportional action. So that description is somewhat clear to me, but if I want a more detailed description of what it is, I can scroll down and we actually elaborate on each of these quite a bit. So that one in question was the man reset value. And if we look at it down here, there's a much better description. So it looks like if we have the integral set to 0, so if we're just doing a proportional band control, then we can use this. In our case, we're going to be using full PID control, so we can just leave that at 0. That was the man reset val. Okay, the next one is MV tracking switch. We're not going to be using this one. This is just on-the-fly manual control. So we're just going to make that false and the tracking value 0, since it's not something we're going to be using. I could have left both of these blank if I wanted to. I just, as I mentioned before in another class, I like to have data on every parameter of everything. Okay, so the next one we have is the stop manipulated value. And it is the value that is set to our output when instruction execution is stopped. So when I shut off this PID loop, do I want it to go to 0 or do I want it to go to a certain value? In this case, I'd like it to go to 0, because when I turn off the oven, I don't want the oven to be warm at all. So this is specified in a percentage, which is something, I'm not going to say unique to Omron, but perhaps different than a few things that you guys are used to. So it's a percentage of our output instead of a hard-coded value. So if my output was 0 to 100, and I specified 10% here, then that would be 10. But if my output was 0 to 300, and I specified 10 here, then it would actually be 30. So that's something to keep in mind. We use that in a few places. Our hysteresis is a percentage of our output full scale. What was that? Yeah, stop MV, 0%. Next one we'll look at is error MV. So if there's ever an error in the function block, the input goes beyond the scaling range, or something happens outside of the block that gives a bad value on something, we can actually have this fail to a certain value. So this is something that I used to use in the water wastewater world when I was doing integration. On our distribution side of things, you never want your distribution to stop. That means you have to issue a boil water advisory, and it gets messy, paperwork. So I would have a value that would allow distribution to keep going, keep our distribution pressure up, but it wouldn't be it wouldn't be controlling itself. The PID loop would be just holding that value until we could figure out what was going on. So I'm going to actually enter a different number here, and I'll just pick a value, 44%, we'll say. This is also a percentage of full scale. So it's our error NV. Okay, the next one is our alpha, it's called. So this is a set point filtering parameter. If we were using a cascading setup, we could actually filter the input slightly. We're not doing a cascading PID loop setup, so we're just going to enter the default on this one. It doesn't really matter. We don't have to enter anything, but I'm OCD about empty parameters. So we'll put 0.65 as the recommended default. Okay, we are getting close to the end. Now this is, if there's one parameter you guys remember today, it is going to be the auto-tuning calculation gain, AT-calc gain, it's called. So what this is this determines how reactive auto-tuning is when you use auto-tuning. Now, you guys may not use auto-tuning, and then in that case, this really doesn't matter, but auto-tuning, according to this parameter, is going to be very responsive at our low end, which is 0.1, and it's going to be very smooth and not nearly as reactive at the high end. So from my experience with this, stick closer to the high end, at least start there and work your way down, because it's quite reactive down at the low end. So I'm going to actually make this 10, which is the least reactive. And for this example of an oven, we're not going to get a very fast response to our changes, the two changes in our output. So 10 is good for that one.
Stuart?
Yes.
For the alpha, do you want to enter that as a real?
Yes. Good catch.
That was Byron. Or Brent, oh. Sorry, not Byron.
Brent, yeah. Yeah, thanks, Brent. I said 10 for this one. Okay, one last member of this structure here, which is the auto-tuning hysteresis. So hysteresis, for those of you who don't know, is deadband, basically. So if my set point is 25 and I have a hysteresis of 1, then I have a window, a deadband of ±1, where I'm not going to try and correct that value. This is useful. Your PID loop is going to be constantly trying to hit the set point, but in reality, it will never actually hit the set point. We're always going to be a tiny fraction of a number away from our set point. So what our deadband does is it gives a window where the PID loop will ignore a slight variation, and that just helps stop tiny little bits of chatter and constantly throttling a valve or throttling a motor up and down. So I'm going to stick with the default recommendation here of 0.2, and this one is again a percentage of our output, so keep that in mind. Okay, so those are all of our operator set parameters. And we've got one more to go, which are the initial set parameters, init set parameters. So I'm just going to cut and paste this rung, delete the logic, and change the comment to setup init params. Before we dive into that, does anybody have any questions so far on what we've done, or having any issues or errors? If you've got a red line in front of your structured text rung or your PID rung, then you should probably take a look at that now. Okay, so we'll get going on init parameters. And again, in the help file right below the operator set parameters are the init set parameters, and thankfully there's only 4 of them here. So the first one being sample time. And what the sample time specifies is how frequently we execute this block. So their recommendation is 100 milliseconds, but we could do this every 100 seconds if we wanted to. If this was really not an important calculation or not a very responsive process. So this will allow us offload some of the processing from our primary periodic task if it's not required. Now our processor is still going to be executing all the other logic at every task interval, but it's going to do, I mean, for example, we've got a 2 millisecond task time in our controller, and if we had a 100 millisecond sampling period set here for a PID loop, then every 50th cycle we would actually do our PID loop calculation. So I always stick with the default on this, 100 milliseconds. On the rare circumstance that you were approaching the watchdog timer on your primary periodic task, you could adjust it, but I've never ran into that issue personally. So we'll stick with the default on that. And this is a time data type. So if you remember from setting up some timers, we specify our time data type. Oh, I already have this one in here as T pound, and then auto-filled something. T pound 0.1 S. So we specify our time data type in actual units of time. Seconds, milliseconds, minutes, hours, whatever we're looking for. Okay, so the next one down, we have the lower limit of the input range and the upper limit of the input range. And this applies to both the process variable and the set point. So since our inputs and outputs are all going to be 0 to 100, I'm going to put 0 to 100 on the low and the high side here. And our last parameter, this is common across every platform I've ever worked with PID loops on, is direct acting and reverse acting. So by default, false is reverse action, which is actually what you would use in a heating application, and true forward action is what you would use in a cooling application. So you increase your output to decrease your input, versus the default of reverse action, where you increase your output to increase your input. Okay, so now before I get too far ahead, I'm just going to go up to my project, check all programs, and make sure I don't have any critical errors in everything I've done so far that could cause for an even bigger error down the road. So we're good. If anybody has any errors, just let me know. Otherwise, we'll continue. Okay. So the only other required parameter that you'll need is the starting value for your proportional band. We can work without an integration time, or your I factor, it's commonly called, and we can work without a D time, or a D factor, it's commonly called. But our proportional band, we do need something there to start. We can do this once we run the simulation, just type a number in there. But what I'm going to do is show you guys how to do something on first scan, it's commonly called in the Rockwell world. So in Omron, our first scan bit is P underscore first run. And then we're just going to move a starting value into our P band, just to get rid of that. It will cause an error on the function block if we don't. So I'm going to add a function, and it's going to be a move instruction. And I'll just put a value of 1 into my P band. That'll just move it once on startup, and then we can take this out once we actually have this thing tuned and we're not needing to do this anymore. But for the sake of the simulator, we don't retain any values. So since you guys are just going to be simulating this, I'm going to keep this here. In the real world, this is not something you do. You would use a retained value and you would just type it in directly. But this will make our lives easier anyways. Okay, so I want to make sure that I don't get any errors on my block. I want to make sure all these parameters are acceptable to the block. So I can just run the simulator without having any feedback on this block. And we can just check that our output turns on. We can switch different modes on the block, and everything's working fine before we proceed. So I'm just going to run the simulation. I had a simulation running on a different instance of Sysmac here. Give me a second. Yes, that's what happened. Okay, simulator's up and running. Sorry for the delay there. I've usually got 5 or 6 different Sysmax Studio instances going at any given time. So you can see here the first run bit moved 1 into my P band, and I don't have an error on my function block right now. If I had started this at 0, I can just manually type 0 there. You can see it causes an error. That error code is 400. And if you looked in the help file, it would tell you that one of the input parameters is not correct. So that's why that's there. So what we can do is give it a set point and a process value, just to see that our output works and we're also acting in the correct direction. So I'm going to give it a set point of 50. If you just double click and type 50, hit enter. And we'll leave the PV at 0 for now. To actually make this block start running, we have to flip the PID start bit here. So I'll quickly set that true. And you can see right away my output, my manipulated variable, my MV, went to 100. So that confirms my PID loop is acting in the right direction. So my oven temperature is 0 and I want to reach 50. I'm going to increase my output to get there. And if my oven temperature was, we'll say 75, and it's trying to hit 50, we should drop down to 0 on our output, which happened. So we verified a number of things here. All of our parameters seem to be working with the block, and we are acting in the right direction. So it's pretty hard to play around with one of these without some sort of simulated feedback. So that's what we're going to do next, is use what's called a moving average to essentially just buffer and average our output and then feed it back into our input. And this will actually allow us to use the auto tuning function. The tuning parameters are going to be a bit out to lunch because it's not a real world application, but it will work, and we can at least see this thing behave like it would in the real world. So we can go ahead and stop our simulator now. Is anybody having any issues? Did anybody get different results playing along?
I'm just getting a few errors here that I'm trying to figure out here.
Okay, you want to read them out?
I think I've got some naming errors, to be honest. A
Yeah.
variable that is not registered. What is that? A bool cannot be converted. Oh, okay, so
Share your screen. That would be a good thing for everybody on the call to see. Those are common errors. So
yeah, let me bring that up here. Okay, you see it here? You see my screen, Stu?
Yep.
Okay, so let me just zoom out here. I don't want to zoom out. There you go. Okay, so I went up to here.
So we got check all programs. And then, so the ones with the red X's beside them in your build window are critical. The ones with the yellow triangles are warnings. So
I did that bit there, the run first.
yeah, so it's actually P underscore first. There you go. Yep.
Oh, is that a predetermined?
Yeah, that's a system variable.
Oh, okay.
Yep. And then now you can go ahead and delete the one that you made, because I think anything with a P underscore is reserved. So you can just go ahead and delete that P run first. It's got it's pink, which means it doesn't like it anyways.
Okay. Okay, good to know.
And then you can check it again. Okay. Input parameter types cannot be converted. Okay, so what data type is P band on yours? Oh, it's a Boolean. Okay, go back to your logic and let's see what, scroll down a bit. Okay, so your P band should be a
Oh.
real.
Should be a real. Okay. Do another quick check.
Okay, yeah,
These
that's
are
all.
all from the other ones here. So, or yeah, what are these?
So they're from this one, but they're
Okay.
non-critical.
I've got two programs in here. I've got one that I was doing for the motor control,
Okay,
and then this heat. So okay, so that looks good.
yeah, so you can go ahead and try your simulator.
Oh,
Yeah,
look,
sometimes it wants
tells
you
me after.
to rebuild it. Yeah.
I can't tell if it's building it or not. That's not liking me today.
What's the difference between build controller and rebuild controller?
Rebuild is from the ground up, and build is just what you've got open and what you've been working on. So rebuild is useful if you've lost some links to system variables. I'm not sure if you remember from a few days ago, I had an issue where I had a duplicate name and it was being used deep in the system variables. So a rebuild it's a much more thorough build. It looks at deep system links. It looks at all your typical stuff that build would do, like global variables, typical troubleshooting, and what's the word I'm looking for? Errors and code errors, basically. So does that make sense?
Yeah, that was good. Thank you.
Weird. I'm getting an issue about memory.
Oh, in your computer or in?
No, when I try and toggle this, failed to write. Check if the variable or memory area is allowed to.
Yeah, so that's a system variable. So you can't toggle that one, but the user variable that you created, the PID on, you should be able to toggle that one. There you go.
I see. So when does this P first run? Is that when the PLC turns on, essentially?
Yeah. So in the real world, that would be when you first enter run mode.
I see. Okay.
Yeah. So yeah, you can go ahead and give it a set point.
Oh, sorry.
Now of just give it a set. Oh, Pete, you can leave it at 10. It's fine. Just make your set point now higher than 10. Okay, so you should have some output now, but you don't. Your P band is 0.
Yeah.
So just change that to a 1. You can just double click on, yeah, you could do it there too, hit enter. Now retoggle your loop.
Like here?
So just change that off and on, yeah. Okay, now lower your set point to 5 or so, just so it wants to increase its output. Interesting.
I'm gonna go back and check my settings just to see, make sure I did everything okay. Let me stop sharing here and I'll go do that. I'll troubleshoot.
Okay, I'll expand mine just for a minute or two here. We're coming up on halfway anyways, so why don't we just take a coffee / bathroom break right here. You can double check the parameters in yours, and then we'll follow up after the break here. So we'll go, it's 1:48 my time. We'll go to about 1:55. Let's reconvene, and then we can keep going. Okay, we're close enough there. Chase, did you get your simulation working properly?
No, it's still not working. Not sure what's going on here. It all matches your text like ST.
Mhm.
But nothing like. So can I just see you go through the simulator on yours?
Sure. Okay, so first thing I do is make sure that P-band was written to successfully. That's a 1. I'm going to give it a set point of 55. Anything higher than the PV. Nothing should happen yet because I haven't turned on the block. So when I flip this bit, my output, my MV, should go to the maximum of 100. So there it's at 100. Now if I increased my PV to say 75, then it should drop off to 0. And it does.
So when I start my simulator, the P-band doesn't automatically write to 1.
Interesting. It should be okay. I mean, you can just turn off your PID block. You can manually write 1 into your P-band, hit enter, and then start your simulator or your PID loop again. And then you can play around a little bit with our variables here, and we still get the same reaction on the output.
Strange. Yeah, I'm not getting any output. That's weird. I'm going to restart my Sysmac and give it a shot. Because you never know.
Your simulation, did you by chance run your simulator in program mode?
Let me check that.
We just stop the simulator, close the simulation window altogether, and then just restart it and make sure that it's run instead of run in program mode, because it almost sounds like logic isn't executing in yours, especially if that 1 wasn't sent to the P-band.
So where do you see if it's in program mode or not?
I've never run it in program mode. I've only ever run it in run mode. But let me try and see what that looks like.
Because I'm just going to like F5.
It'll tell you right here.
Oh, okay. Online simulator, ERR, run mode.
And then if you wanted to switch it to run mode, you can just go to controller mode, run mode, just like you're online with an actual PLC.
Okay. Yeah, strange. You can carry on. I'm going to keep toying around with this.
Okay. Yeah, we can take a look after too. I could take control of your end and do some digging, but sure, we'll move on. So everyone can stop their simulators now. You can leave the simulation pane open, that's fine. We don't have to close that down. But what we're gonna do now is simulate some feedback so that this is a bit closer to what would happen in the real world. And then we can also, this will also allow us to use the auto tuning function. Prior to working with Omron's PID loops, I never touched auto tuning PID loops. They were just overly complicated, I found. And I was kind of a do-it-yourselfer, so I always tuned them manually. But I quite like Omron's auto tuning capabilities, and we only have an auto tuning PID function block. So it's there, you may as well use it. So what we're going to do is we're going to take the output of this PID block, which is our MV. I've got mine tagged as oven MV. And we're going to use a floating average or a moving average to essentially put a delay in the value of this. And then we're going to feed that back into the input just to simulate a slight delay in the process. So if you go to your toolbox and you type average, we've got a moving average function block. So I'll add a rung here. And I will add my moving average function block to the rung. It's actually a function, it's not a function block. You probably noticed I don't have to name the actual block. I don't have to give a tag to the actual block. That means it's an instruction or a function, not a function block. Just a terminology lesson there. Now, I'm not going to dive too deep into each of these, but if you mouse over, they're all pretty self-explanatory. If you've worked with moving averages before, it's probably has a lot of familiar inputs and outputs. So the input value is going to be the output of our PID block. So in my case, that's oven_MV. The current index is the input value storage position. And this you don't actually have to write anything to, but it does need to be a variable. So I'm just going to call this index. And this will just increment. You'll see it change as it populates the moving average block. We don't have any involvement with the index variable. It just needs one. So the buffer, this is going to be an array that it uses to store the data before it does every average. So two conditions of the buffer. One is the array needs to be of the data type that the in variable uses. You couldn't average a real value with an integer array. Lose a lot of precision. I don't know if it would even let you run the program, to be honest. I've never tried. So that's the first condition, the same data type. The other condition is we need to have enough spaces in that array for the size of the buffer. So I'm going to make, I'll call this my PID buffer. And because it's not a specified data type, it's going to ask me the data type, as well as do I want it to be internal or external. So I'll choose internal, and I want it to be a real, of course, because that's the data type of what's going into the moving average block. And I'm going to give it 100 array positions because I'm going to be buffering 100 points in this floating average. Now the buffer size has to be less than or equal to the number of variables in this array. So I'm just going to use uint #99 to be safe. Oh, I should also add, we need to specify an array position, not just an array. So we'll start at 0. Q doesn't really matter. That just means the calculation was successful. Since this is going to be executing over and over and over again, we know it will be successful. We don't really care if it is or if it isn't. It'll be blatantly obvious. So we'll just put a variable there to make it happy. Now the actual value of our moving average comes out here. Calculation result is what it's called. So we are going to put the actual PV here. So this will be my oven PV. So we're taking this output, we're doing a floating average calculation, and our floating average is fed into our PID loop on the next scan through this code. With the moving average block, I'm going to slow it down a bit. Even 100 points is done far too quickly in these PLCs. So we have some instructions in Sysmax Studio where we can access time bits You do it a lot in like a compact log or a micrologic, sorry, you access the timer bits so you can get seconds, milliseconds, that sort of thing. So in Sysmac, I just type get. We've got a bunch of different clock periods that we can use. So I'm going to get the 100 millisecond clock, and I'm just going to drag it before this. And then 10 times a second, we're going to perform a floating average, which makes sense because this block executes 10 times per second as well. So we're keeping it consistent with the execution of the PID loop. Anybody having any issues so far with that?
Yeah, I'm just doing a rebuild because I've got a red bar in front of my rung.
Okay.
The array of real cannot be converted to any num.
Did you specify on the buffer an array position?
I guess not. What? Pardon me. Oh, I see. Not just the name of the variable, but actually an index position. Okay.
Index position.
Thank you. Yep. The red line went away. Thank you.
Perfect. Okay, so let's fire up our simulators, and we can now do some actual tuning. So before we start it, let's give it a set point of whatever you want. I'm going to choose 66. And now we can start our PID loop. And you can see we are getting some different behavior from our PID loop. It's still jumping all over the place because we haven't tuned it yet. So what we can do now is an auto tune. So up at the top of our PID block, we've got two Boolean variables that we put tags on. One is our manual control. One is our start auto tune. Start AT, it's called. So when we flip start AT, a few things are going to happen. The first will be this AT busy bit will go true. That means that it's in the process of auto tuning. And when that's finally finished, AT done is going to go true. So the first thing I'll do, because we've disabled the I and the D in this by having them 0, is I'm just going to type 1s for 1 second here on my I time. I'm going to type 1s on my derivative time, my D time. And now I'm going to flip this bit true and let this, it'll jump around a little bit, but it was very quick in the simulator because my feedback loop was too perfect. It's not really real world conditions, but you can see all of my parameters now, my P band, my I time, my D time, they've all been tuned. They've got 60 milliseconds on my D time. I've got 1.4 seconds on my I time, and my proportional band has settled on 515. Now we can play around with our set point, lower it, raise it, and you can see the output now is much smoother. We don't overshoot, there's no hysteresis. We're approaching it very slow, which is something you'd want to do in an oven. But if this were, say, a pressure washer, where it's very quick to react, we would actually adjust our AT calc gain parameter here from 10 to 5, something like that. You can try different ones as you tune it. 10 is very slow, very smooth, which, as you can see, this is a pretty smooth, pretty slow to respond PID block. That's something that we want for an oven. And you don't have to flip the start auto tune bit false, but I like to. It's not going to re-auto tune until you flip it true again, so it auto tunes on a rising edge. You guys are welcome to change your set points around now, see how it reacts. Is anybody having any difficulties? Is everybody's PID loop appear to have tuned properly?
Stu, I'm getting an error here. That's I'm still trying to sort this out here, but it says the array of real type cannot be converted to any num.
Yeah, I think that was the same one Brent had. So put in specify an array position in this buffer variable here.
Okay, so you just did a 0.
Yeah, just put a 0. Did that work for you, Chase?
Yeah, it got rid of the error, but
Okay.
my PID still isn't working. So.
If you're done the material you wanted to cover today, I'd be interested in watching the troubleshooting.
Yeah, that's all I really wanted to cover. I was going to show, and you guys don't need to play along with this, but like I said, the one thing I want you to remember about auto-tuning these things is this AT calc gain. So that was 10, right? That's very smooth, very slow to react. By default, it's really quick. So I'm going to make that 1, and I'm going to rerun this simulation. And it's probably going to be too reactive to even auto-tune. So I change that to 1 now, making it super jumpy. I'm just going to give some starting values here. Turn on. Give a set point of 50, we'll say. Now I'll try my auto tune with that new parameter in there. So now if you look at my output now, I am either 0 or 100. I am not gradually going in between 0 and 100. It's all or nothing. So very responsive. Surprisingly enough, my PV is actually tracking pretty closely to my SP, but this is not something you would want to do with a VFD or a valve. You get the idea. So part of tuning is finding a calculation gain parameter that works if you're going with the auto tuning method. So if you write down a note about anything today, make that the note. It can save you a lot of time. Okay, Chase, why don't you share your screen? I can take control.
Okay, let me, yeah, I just want to stop sharing there. Perfect. So we're in here. Give you control. There you go. Have at her.
Hello?
Yeah, I'm,
No.
there we go. Okay. Yeah, there's, it's kind of, because Zoom isn't run at the administrator level and Sysmac is, I don't know if I'll be able to, but I will try. Yeah, it's not letting me do anything with Zoom. I'm going to jump out of the meeting for a sec. I'm going to launch Zoom as administrator, and then that should let me control it.
Okay.
Can you go to your tasks?
Or do you want it in the config?
Yeah, in the configuration section there. Yeah, go to your task settings, then go to where I'm. Can you see me moving the mouse?
No.
Okay. Go down to the third one down. Okay, so you have program 0 in there. Good. So right click on where it says heat PID, where you've named the program, and move that up. Okay, now start your simulator.
That didn't change again.
Yeah, you're in run mode, which is good. Yeah, it's like your logic isn't executing. Is there?
If I go in here,
Okay, so right click on program 0 over there. Sorry, stop your simulator. This has to be done offline. Now right click on program 0 and go to settings for debugging. Okay, it's disabled. Good. Oh, you enabled it. Yeah, you want that disabled.
okay.
I don't know how relevant this is, but I noticed that his moving average is writing directly to the input parameter of the PID rather than the variable we assigned to it.
Oh, this one here?
Yeah.
Yeah, that does need to be changed. The thing that's throwing me off is that that move instruction isn't moving anything into his P band variable.
Let me delete this rung completely. How do I move that rung up?
Pardon me?
How do you move this line up?
I just delete it and move it above when you create it. So if you right click on the 2 there, or you can insert it below from the one above, yeah. So you start typing P, yeah. And then just hit I. If you click after type I and then MOVE, type real #1. That should be your P band, yeah. Okay, so now go up to your controller at the very top and change it to program mode and then change it back to run mode. And that should toggle that first run bit. Interesting.
Strange. Let me try and change that bit name. That's variable name.
That's what I called mine. Yeah, try a new variable name. Sure. I'm wondering maybe did the duplicated variable name thing.
E band. I'm not a boy band.
No. I think P underscore band is reserved because it starts with a P underscore. So just band 1. Yeah, that works.
Oh dear. Okay, it automatically
That
changed.
one updated, yeah. Sorry, you moved pretty quick there. Did you rebuild the controller?
I'm just doing that right now. Sorry.
Okay.
Quick run. Very strange.
It looked
Yeah.
like you hit build rather than rebuild.
Oh, I gravitate towards. Is there a difference between build and rebuild?
Yeah, rebuild is much deeper.
More in depth? Okay.
Yeah, it's kind of hard to explain, but takes a bit longer. But if it does seem to fix those stray variable associations that can happen.
Okay, good to know. Takes a lot longer too.
Yeah, it does.
So that P first run bit, does it automatically just toggle that on off, or will it set that on when the controller turns on?
It's on for the first cycle, but it happens so quick that you won't see it.
Okay.
Yeah.
But the move command will hold, is like if it's toggled once, it'll hold that move.
It'll do the move once, but nothing else is writing to that P band, so the P band should retain that value of 1.
Okay.
Because once we do auto tuning, we need to write to that P band with a new value. So we don't want to hold that move because it'll constantly overwrite whatever we're trying to do with our auto tuning.
Oh, fair enough. And why do we need to make that move?
It needs to have something other than 0 to start. That's all.
We can't have it just like an initial variable be 1 to start to get rid of that line altogether, or?
Well, that's really what that line does.
Okay.
If you had an actual PLC, you would just type 1 directly on the block and it would remember it.
Oh, okay.
And then when you do your auto tuning, you're going to save all those new parameters anyways. So
Yeah.
this is just kind of specific to the simulator to save people a bit of hassle.
I see. Okay. Yeah, same thing. Strange.
Yeah, if you scroll up a bit, none of your constants are getting new values either. They're all 0. So everything you're trying to force constants onto, like in your operator set parameters, none of those are. So yeah, it's like your logic isn't working. Interesting.
I'm going to delete this just in case it's caused by something in that program. I was messing around with the other program after we had finished up, so I'm hoping that maybe there's something in there that caused an issue. For the most part, if any of you guys are still interested in going through the troubleshooting, feel free to stick on. But for the most part, you guys can take off if you've gotten everything you need to get out of this. So, and again, thanks for joining for this last session.
Yeah, you guys all have a good starting point template for PID loops.
Do you want to maybe try a branch around that move so that the P first run also sets some kind of latching coil just to see if the P first run ever even does turn on.
Yeah, good point.
It almost looks like there's an issue with execution, like that whole section may not be executing.
It is the whole section, yeah. If you look up at the structured text section where we're writing constants,
Yeah.
The variables don't get new values. So
Right.
yeah, it's definitely an execution thing.
All right, next time I'm just going to do a build. How's everybody's week?
You know
so
what?
far?
There's a checkbox next to tasks.
Yeah.
Check that. Your primary task and your program 0 are unchecked. I think you have to stop the simulator for it. Yeah. Now, oh, too many clicks. Now ready, simulator?
That's all it was. I'm going to laugh.
I'm both hoping that was it and that wasn't it.
Yeah, you'd think something that simple wouldn't just be hanging out in the menu there.
Yeah.
Oh, that was it.
That was it. Yeah.
No
So,
way.
Good news is that's specific to the simulator. You can't do that on a real PLC. Okay, so yeah, test your loop out now. Okay, so bump your set point up to say 50, whatever, higher than your PV. Turn on your block.
There we go.
Your output throttling, so you can do an auto tune now. Or sorry, give the 3 tuning variables there, the proportional band, the integration time, and the derivative time. Give them 1 second on the 2 time.
Okay.
Yeah, so just 1S. Yeah, and then 1S on that. Now you can flip the start AT bit.
So the auto tune won't override if you have 0 on any of those parameters. They have to be non-zero to be auto tuned.
I've never tried the other way. I just know that setting them to 0 disables either integral or derivative mode. So
Right.
that'd be something I could find out pretty easily.
So I triggered the start AT.
Yeah, and looks like your floating average block isn't doing much right now.
What does yellow mean? It means it's not being executed, or?
No, it is.
Okay.
In the simulation, the
Yellow logic. Hmm.
Yeah, he's got false for success.
Yeah.
Now it's successful. I overrode it.
Mouse over your PID buffer variable. Oh, that's an array of 2.
Oh, okay.
So go, yeah, there you go. And you can just change that to 0 to 99. Okay, that should take care of that.
Okay. Now we just go rebuild, or just build, not rebuild.
Just build.
Much quicker.
For little things like that, I'm not sure you even need to build it, but doesn't hurt. Oh, Canada Revenue Agency's calling me.
Oh, good. Looks like COVID hasn't affected them.
Yeah, maybe I got another tax return coming in.
Okay, so
Yeah, give it a set point of. You won't be able to write anything to the PD now because it's being overwritten by that floating average. So you can write a set point of say 50, give it 1 second on the 2 time tuning variables. Then start the block up. Perfect. Now do an auto tune.
There we go.
That's it's still a bit jumpy. So you can actually run it again if you wanted to. Did you have that parameter? No, you can leave that bit on pretty much all the time. Yeah.
Okay.
You could just toggle the auto tune bit false and then true again, and it'll redo your tuning.
I assume it's still populating the array of 100 in the moving average. So that might be why it starts out jumpy.
Yeah, yours seems to be super fast. That might be just.
Oh, it might be because of this. My simulator goes like crazy.
Yeah. Just scroll up to see what that AT calc gain parameter is. No, you're set to 10. Okay.
10.
Got the 100 millisecond clock. Good.
My PID buffer, that's right.
PV is your output. Buffer your index. Everything looks right. It's very jumpy.
Everything in here is okay? 0 to 99? That was right?
Yep.
So I assume anytime that you turn off the start AT and then turn it back on, it reruns the auto tune for a new set of parameters.
Correct. Yeah, it'll reattempt the auto tune.
Will it, so every time you cycle power on the PLC, will you need to auto tune, or can you make those variables retained?
No, it'll retain them.
Okay. Do you have to do anything for it to retain, or is it just automatically like that?
I don't believe on the PID block you do.
Okay.
No, there are things like the PID block, the retentive timer block, that they'll be retained for you.
Okay. All right. Well, I'm going to stop sharing.
You can play around with it, Chase, if you want. Try to smooth it out a bit. It could be the time base that you're using as well.
Well, I know my simulator goes super quick.
It does, much quicker than mine. Yeah,
Mm-hmm.
it's kind of weird. But anyways, guys, anybody have any questions before we wrap up here on what we did? Any issues you've ran into?